This meeting is being recorded.
Okay, so very good afternoon, class. In last lecture, we were talking about the ratioed logic, right? So, what is a ratioed logic? So, first, the goal or the motto behind this ratioed logic is to reduce the number of devices over complementary CMOS, right? Whatever the number of devices required to design a particular logic design. So, by using a ratioed logic concept, you can reduce the number of devices required to design or to build a same design. Now, what are different ways to achieve this? So first you can go for a resistive load, right? So you have pull-up network that you can replace by the resistive load, and you can give input to the PDN. So total entire pull up network, that is PMOS. Now the question may come to your mind, why only we have replaced the PMOS and why not NMOS? Because the PMOS, it always consumes more power. The PMOS always consumes more power, and that's why we have reduced and replaced the pull up network part based on PMOS. As compared to NMOS, PMOS always consume more power. Its static power dissipation is more as compared to pull down network. Why it is so? Because PMOS, see where we have connected PMOS to VDD, right? To the plus supply. And where we have connected the pull down network NMOS to ground. So, but obvious, PMOS as it connected to the VDD will consume more power, right? So you can go for a resistive load. Second part is you can go for depletion load, right? You can go for the depletion load, or you can use the PMOS load itself. Only one PMOS, right? So this is a pseudo NMOS. Okay, so by using this resistive load technique, or using the depletion load of NMOS, or pseudo NMOS, either you can use or choose any one of the technique to reduce or replace a PMOS, so that the overall number of devices will get reduced over a complementary CMOS. And that concept or that reduction is known as ratioed logic, right? चौथ्या युनिटची आज without before leaving, everyone has given minimum 20, 20, 25, minimum 20. Okay, now this is the again how to calculate this resistive load. If suppose we have used the first technique, by we have replaced that PMOS using the resistive load. So how to calculate that? So the total VOL is equal to RPN divided by RPN plus RL, right? It's a asymmetric response. And static power consumption, TPL, transition propagation delay, right? How to calculate that propagation delay? 0.069 RL into CL, RL into CL, right? So basically the load, it is contributed by the N transistor, N type transistor, and the load, resistive load, whatever we have connected. So this is how you can calculate VOL, then TPL, and all the different parameters. Okay, now the active load. Okay, so first one is a resistive load, active load. In that active load, we have two types: depletion load and pseudo NMOS. So this is what the depletion load means. What you can use the NMOS whose threshold voltage is less than zero. It's a depletion load NMOS. And regarding pseudo NMOS, you can attach only one PMOS, but whose gate is connected with the same potential as that of NMOS. Where NMOS we have connected to the ground. So the gate of PMOS also connected to the ground. So that becomes the pseudo NMOS. That means आपण त्याला सिंपल लँग्वेज मध्ये काय म्हणू शकतो की आभासी आभासी एनमॉस सारखं ते काम करतं दॅट इज सुडो एनमॉस सो दीज टू कॅटेगरी कम्स अंडर ऍक्टिव्ह लोड अँड प्रिव्हियस कॅटेगरी इज resistive load. Okay, so any of the method you can use for the ratioed logic concept. Now this is what the load lines of ratioed gates. Okay, you can see here this is of resistive load, this black line, then this is of depletion mode, and this is of pseudo nmos, right? This is of pseudo nmos. So it's a il output current, load current you can say, and on x-axis you have a
आतापर्यंत 1.5 GB संपलेला असत
you have a
आमच्या तिथं जिओला
v out. Right now, load line of ratioed log gates. So this is the actual comparative curve you can say. Next part is now the pass transistor logic. What is pass transistor logic? Now, pass transistor is what actually itself is a CMOS. Okay, you have a PMOS as a pull-up network, NMOS as a pull-down network, and instead of a single NMOS or PMOS, you can use the parallel connection of that PMOS and NMOS that forms the transmission gate, or you can say a pass transistor. When you connect parallelly PMOS and NMOS, see for the CMOS inverter, how we are connecting in a series. PMOS and NMOS are in series. But what happens if the PMOS and NMOS are connected in a parallel? That forms the pass transistor logic, right? That forms the pass transistor logic. So this is the symbolical representation of transmission gate, or you can say pass transistor. Don't get confused between the transmission gate and pass transistor logic. It is one and the same, right? You have a NMOS here, you have a PMOS here. These are connected in parallel, right? Their source you are making common, and you are giving input to the source terminals, and from its drains you are taking the output, and to the gate you are providing a clock pulse that forms the transmission gate, right? Now these are the different examples based on the transmission gate. So this is how you can design the multiplexer. Okay, this is a b, this is s, and this is the s bar. So it is a parallel combination of first transmission gate, it is parallel combination of second. See, always remember, in transmission gate PMOS and NMOS are connected in always parallel combination, always, right? Always parallel combination that forms the transmission gate. Clear? And at the output you have an inverter, right? At the output you have a inverter that forms the multiplexer. So this is a multiplexer design of using transmission gate. Okay, this is how you can, this is the design of XOR gate. Okay, XOR gate transmission you can say here. This is a XOR gate transmission. This is transmission gate of full ladder. Okay, it is a transmission gate of full ladder. It is a P, it is a CI bar, CI. Here it is CI bar. It is a sum generation, it is a carry generation. You can have a look on this. right? So it's a transmission gate full adder. Now, next part is a dynamic logic. Okay, whatever we have studied, it is of the static, right? Or you can say a combinational logic design, or in that static logic. Now, next part is a dynamic logic motivation. So, why to study this dynamic logic motivation? So, in case of this complementary CMOS, what are the advantages of this complementary CMOS? So, VOH is equal to VDL, VDD, and VOL is equal to ground. There is a no static power dissipation. Why there is a no static power dissipation in complementary CMOS? Because the entire PMOS we have replaced with either resistive load or active load, right? In active load you have a pseudo NMOS and depletion type NMOS, so that you know, right? Now, fan in and fan out, or you can say for fan in of n transistor, two n transistors are required. That is the drawback. And series networks unavoidable. So you have to, if you want to go for a complementary CMOS logic, and in that you have to design some dynamic logic. So fan in fan in concept is, or the fan in of the transistor is more, so that the power consumption will be more, and series networks are unavoidable. You have to use some series networks. Okay. And what about the pseudo NMOS logic? So in case of pseudo NMOS, fan in for n transistor is n plus 1 only, and above is twice into n. That's the multiplied by 2, double of the n. Here only one more transistor of n it is required, so it's advantages. Series networks are avoidable in case of pseudo NMOS. And what is drawback then? VOL is not connected to the ground, and there is a static power dissipation. So in complementary CMOS there is no static power dissipation, but in a pseudo NMOS logic there is a static power dissipation. So this dynamic logic, actually it is a combination of two design approach. Which two design approach? So for a simple design you can go for your normal CMOS logic, and for the complex design you can have that CMOS as well as complementary CMOS or pseudo CMOS. Both options are available. So overall you can say dynamic logic is a combination of two design approaches. What is basic principle of this phi n network? Okay, pull down network. So you can say here is a PMOS. You have pull down network, and again to that pull down network you have a NMOS, extra NMOS connected. So what happens when clock is equal to L? It is pre-charged. That means Mn is off, MP is on, and this Mn is off. That's why this Y can't go down to ground, right? This Mn is off. Off means what? Off means what? Open switch. So it is total open part. So the current will go from the VDD to output. As MP is on, that means it is a closed switch. So why it is pre-charged to VDD. And when this clock is at H, H for high and L for low, right? When the clock is low, only MP is on, this will be off. That means it is a closed switch, it is open switch. So Y will pre-charge to the 1, and this Y can't go down because this is total open circuit. And when the clock is go high, that means for evaluation, then what happens? When it is go high, now this part will be open switch and this part will be closed switch. Now here in this case, Y can go down to ground or stay at VDD according to PDN evaluation, right? So this Y can be grounded or it can hold to the VDD according to what is pull down network evaluation. What is pull down network? What is the input to the gate of pull down network? Based on that, it can go to ground or it can stay at VDD. So it is a basic principle of phi n network, pull down network, you can say. How the basic principle of P network, pull up network, you can say the same logic. You have PMOS, then pull up network output, and then NMOS. Okay. Now, again, when clock is low, this MP is off. When clock is low, this MP is on, right? When it is low, it is MP is on, MN is off, right? So Y can't go up to VDD, Y is pre-charged to ground. Okay. And when this clock is high, when this clock is high, then MN is off, MP is on. Here the Y can go up to VDD or stay at ground according to pull-up network evaluation. Based on this pull-up network evaluation, it is either charged to the VDD or to the ground, right? So when it is low, it is called as pre-charge condition, and when it is high, it is a evaluation. So it's a basic principle of P network. Okay. Now this is a pi n network operation. Okay. So this is a pre-charge. When clock is low, Y is high, right? And for evaluation, when clock is high, the Y either can be at high or low, depending upon this middle condition. So it's a pi n operation. Similarly, it is a characteristics of pi n network. So what are the characteristics of pi n network? So logic of pull down network consists of NMOS transistor, that is Y is equal to AB plus C bar, and number of transistors are required N plus 2. Fastest switching speed due to reduced number of transistors. Which transistors? Overall transistors. And ratioless logic, that means VOH is equal to VDD and VOL is equal to ground. No static power dissipation, only dynamic power dissipation. But what is drawback? Reduced noise margin, right? Noise margin is reduced. This is the only drawback of this pi n network. What are the problems with this phi n network? Leakage current. This is the first problem. Which one is leakage current? What is this leakage current problem? So the I leakage is equal to I reversed bias diode plus I weak inversion. So it is current contributed by the reversed bias diode, whichever is the reversed bias, that is IRD, and IWI, that is weak inversion region. So leakage current is the big problem issued, or this big problem that is addressed by this pi n network. Okay. Or this is a problem related with this pi n network, leakage current. This is the first one. Okay. Next is a charge sharing. What happens to this charge sharing? When there is a clock and when it is a it will be high low, that means pre-charge evaluation. So what will happen? So before this a rise, this qi is equal to cl into vdd plus ca into 0. And after a rise, that means this a will become to the high level, this q2, this q2 is equal to cl plus a ca into vy. So if you solve these equations, you can land to the conclusion that vy is equal to cl divided by cl plus ca into vdd. That means these many capacitances are associated, and these capacitances are responsible for the charge sharing. These capacitances are the responsible for the charge sharing, right? Now this charge sharing ripple is the new concept. How to calculate this charge sharing ripple? Delta vcs is equal to vdd minus vy is equal to ca divided by cl plus ca into vdd. So by the same equation, and what is this ca upon cl plus ca? So these are the capacitances associated with this circuit. This cl is the load capacitance, and ca is the intermediate capacitance of this a, or you can say it's a load capacitance of the a transistor, right? Clear? So it's a capacitances associated with this a, right? A NMOS, it's a Ca, and Cl is the load capacitance. So by using this Cl divided by Cl plus A into VDD, you can get the charge sharing. But it is also problem associated with this phi n network, right? Now what is solution to this charge sharing problem? So you can use the static bleeder circuit. Okay, what is this static bleeder? You can say, if this is the capacitance, it is a Cl, so you can add one more PMOS exactly parallel with the first one, right, to avoid this charge sharing problem. Or you can go for some pre-charge of internal nodes. This internal loads, you can go for this pre-charge of the internal loads. So by using these two ways, you can actually address this charge sharing problem, right? Now next problem is a clock feed through. Okay, what is this clock feed through? So this clock feed through is, you can say, it is exactly might forward bias PN junction. It is exactly like a forward bias PN junction, and the output without redistribution. Now consider this example. Here is a clock from low to high, it is transiting. Low to high, it is transiting. So this clock feed through is what? So whatever the output, right? So it is feed through the this phi n network, or the precharge PMOS of this phi n network. This clock get feedback, clock get feedback to this PMOS of the precharge transistor of the phi n network, right? So this is a feed through concept. So it's a V in volt and time in second. So basically this is the mid of the forward bias of PN junction diode. This is the output, and this is the output without redistribution. That means this MA is off, and these are the internal nodes in PDA. So it is a clock feed through. That means clock will get feedback to again to the main precharge PMOS of the phi n network, right? So how many problems we have discussed related to this? Leakage current, charge sharing, then clock feed through, right? And the fourth one is cascading. What is cascading? So outputs are already pre-charged, right? That you know, to VDD, and they drives N MOSFET. So this is the basic problem of the cascading. That means you cannot cascade directly this phi network to the next phi network, and you cannot give the output of previous phi network to the next phi network. This is the major issue addressed by this phi network, or this major issue faced by this phi network. Okay, so charge sharing, this cascading, clock feed through, and the leakage current. These are the four major problems that is faced by this phi n network. Okay, then next part is a domino logic. Okay, so we will discuss this part in the next lecture. But again, very quickly, we will revise whatever points we have discussed. So we have started with the dynamic motivation. So what is the difference between the complementary CMOS logic and pseudo NMOS logic? So there are certain advantages of the complementary CMOS. What are those? VOH is equal to VDD, VOL is equal to ground, and there is a no static power dissipation as we are not using the PMOS. Okay, then what are the disadvantages associated with this complementary CMOS? So for fan in, if you have a n transistor, then for a fan in you require two n transistors. That means exactly double. This is one of the major drawback, and series networks are unavoidable in design. If you are using a complementary CMOS, so you cannot avoid a series networks. Coming to the pseudo NMOS logic. Coming to the pseudo NMOS logic. So what happens in that pseudo NMOS? For fan in of n number of transistors, n plus 1, that means whatever the present, only one more than transistor is required. It's a advantage of this pseudo NMOS. Then series networks are avoidable, right? Series networks are avoidable. But now what are the problems or drawbacks associated with this pseudo NMOS logic? So VOL is not connected to the ground, and as we are using a PMOS, right? A pseudo PMOS, let it be, but there is a some sort of static power dissipation. And always remember, dynamic logic, it's a combination of two design approaches. It's a combination of two design approaches. Okay, so either you can go for a normal combinational logic by using CMOS, or you have to use a hybrid, that means CMOS as well as a complementary CMOS, or in some cases pseudo NMOS logic. For a complex design, you have to choose static logic as well as dynamic logic, both you have to inculcate to build that design, right? Then these are the basic fry networks. So what will happen when the clock is low, that means in pre-charge condition, and what will happen when their clock is high, that means evaluation condition. Then this is a basic 5p network. Then here also again, what will happen if clock is low, that means in pre-charge condition, and then what will happen if clock is high, that means evaluation condition. This is how the phi n network works. Okay, now these are the problems associated with the phi n network. Its equation is y is equal to ab plus c bar. Okay, now what are the advantages? Number of transistors requires are n plus 2. Faster switching speed due to reduced number of transistors. Ratio less logic, that means VOL is equal to VDD and VOL is equal to ground, right? In case of complementary CMOS and fine network, there is a no static dissipation, only dynamic power dissipation. And what are the disadvantages? The reduced noise margin, right? Noise margin will get reduced. Now these are the problems associated with the phi n network. What are the problems associated with the phi n network? Leakage current, this is the one of the major problem, right? Then second one is the charge sharing. Okay, because of the internal capacitance and also load capacitance, the charge is shared by different NMOS. That is the problem associated with this phi n network, that is charge sharing, right? And what are the now how to address or how to resolve this problem? So either you can use a static bleeder circuit, or pre-charge to some internal nodes, or pre-charge of some internal nodes. These are the two way to address this charge sharing problem. Next one is a clock feed through. Okay, this is the third problem associated with the phi n network, clock feed through. And the last one is a cascading problem. Why cascading is not possible? Because because whatever the output of the first or the first stage of phi network, it is already pre-charged to VDD, right? So you cannot pass that output directly to the next stage. You cannot pass that output directly to the next stage because it is pre-charged to VDD. It is pre-charged to VDD. So they cannot directly feed, or they cannot feed directly to the next stage of the phi n network. So cascading is not possible, or you can say cascading, we cannot directly cascade, right? You have to use some intermediate circuit, then and then only you can able to cascade the phi n network to the next stage. Okay, and the next part is a domino logic. Okay, so what is this domino logic? So this part we will continue in the next lecture. Today we will stop here. If you have any doubt or query, you can ask me right now.